good afternoon, and thanks for the introduction. Thanks for letting me be here. I do work for Nginx. I also am owned by 3 cats. I am used to being ignored. I was a football rep for 10 years. I am used to people disagreeing with me. And by the way, I am married. I have a witness that I do not read minds. So feel free to ask questions for this. So last year, I did a little talk here called Know Your Data, the stats behind the alerts. And this talked about some of the things that are behind those things that our systems are telling us around observability. And I'm not going to necessarily talk about open telemetry, and I'm not going to necessarily talk about all those best practices. But something became really clear when I did this talk is that it is really easy to lie with statistics. Anyway, if you remember, some of y'all may have been here for this talk or have seen this other talks, I start off by asking the question, what's the difference between a mean, a median, and a mode? And I keep track of it, and the numbers work out to roughly 79-ish, give or take, believe they know what a mean means, and roughly 52 believe they know what a median means, and roughly 10% believe they know what a mode means. I just lied with statistics. People will believe almost anything if you put numbers to it. And unfortunately, statistics is all about that space. There are lies, there are damn lies, and there are statistics. This is often contributed to Benjamin Disraeli. But actually, the only place this has ever been found was Mark Twain, and I have to read this one. In Mark Twain's autobiography, figures often beguile me, particularly when I have the arranging of them myself, in which case the remark attributed to Disraeli would often apply with justice and force. There are 3 kinds of lies: lies, damn lies, and statistics. People lie with statistics all the time. I will try, not successfully, to stay out of politics and advertising, because they are the leading examples. Like I said, I will try. I will not make it. We live in a data world. Every talk I have sat through today has brought up the fact that we have data all over the place and nobody quite knows what to do with it. But the data can give you some really great, powerful things inside of here. It gives us our decision making based on evidence that's there. It helps us identify patterns. Humans are really good about finding patterns for that things. It helps us manage risk. So it's all these different pieces that come into here. And as Shaw said, really intelligent people can be moved by the statistics. However, it's a numbers game, and a game is just that. It's a game. And that game can be misinterpretation, it can be ignoring margins of error, it can be bias inside of here. What happens is we fit the reality to match the statistics so that when we do this, we're changing the rules. We're now using the statistics to define our reality. So let's start with means. You have a KPI, your KPI is 1 hour per month trailing. Which one of these would you rather report? 1.56 hours or 0.53 hours? These are based on exactly the same data sets. The first one, 1.56 hours, is an arithmetic mean. And the second one is a harmonic mean. They are both means. They are both valid. They are absolutely mathematically valid. Same data sets. And oh, by the way, the middle mean, the geometric mean, works out to 1.01, and the mode for this data set works out to 1. And so you're in the right ballpark. But I just lied, again, with statistics, using perfect math for that. And now, how does that get replayed? Sorry, my data is heavily US-based. I'm US-based, so I know where to find it for this. The current household income per person in the US is $59,000 US. Average household size is 2.63. So the household income is 156. No, the household income is 106.4. It's not. So to have $1 million a year, all you need to have is 14.8 kids, right? Makes perfect sense. This first shows up in 1957 with two magazines that are arguing back and forth about which one had the most valid data. And this is an example they literally used. You know, the numbers were a lot different. There was a $3,000 and a $7,000 rather than the numbers we're dealing with at that point in time. But simply using math, this is a logical progression. Statistics can lie. Deviation. A statistical point without range is meaningless. If I look at you and say the arithmetic average is 17, you have no idea. It could be a range of 10,000. It could be a range where the numbers go from 15 to 20. There's a big difference. The example here, Death Valley, which holds the record for the hottest spot on Earth, hottest recorded temperature on Earth here, has a arithmetic mean temperature difference of 16.1 Celsius. That range, by the way, is 15 Celsius, which is minus 5-ish Celsius, minus 5 Celsius to 104 or 40. You know, 16.1 sounds really comfortable, especially to me coming out of San Francisco. If I walk outside right now, 16.1 sounds really good, okay? But there's a big difference between 15 Fahrenheit and 104 Fahrenheit. So range is really important. The same thing can happen if you're looking at response times coming in from your server. These are messages coming in from a server, small data set. But the standard deviation of A is 3.3. Standard deviation of B is 44.8. They have exactly the same arithmetic average. So there's a unique capability. If someone doesn't tell you what the range is, they're misleading you. Keep that in mind. And then deviation. Your job, if you're going to lie with it, don't deviate. But the problem is that deviation can vary by the sample size itself. That sample size then runs into the category that says, if I'm looking at a single person, I can have a very broad range. If I'm looking at the average, I can have a very narrow range. I have a background in open telemetry. This is tracing 101. Traces are single points. They are single requests. If you look at a single trace, you are looking at a single point in time, a single model. That's great because it gives you that user happiness proxy. But if you're looking at it on a graph, you can't look at it as a single point. You do an aggregation. The more you aggregate, the tighter your range becomes, and the more accurate your patterns look like. And so when you start looking at that, that becomes an equally important phase of knowing what the ranges are, as well as knowing what the sampling sizes were. And that leads us to sampling. Results are only good as your sample data. So let me do a little quick here thing right here. Did you have coffee or tea this morning? Coffee or tea? Okay, that's the example. Coffee or tea? Coffee or tea? 100% of this crowd drank coffee this morning. I've been ignoring that because I'm the guy doing the sampling. I dropped you as a sample. I have 2 people. So even if I added it into this, I could probably argue that you don't count as a quarter, as an actual point. You probably count less than that because you had both. By the way, I also had both this morning. So that's sort of the model that's in here. Sample sizes can be really convenient. 4 out of 5 SREs prefer open tofu. Okay, advertising, sorry, 101. 4 out of 5 doctors smoke Lucky Strike cigarettes. You know how they did that one? They went to a medical convention, and as the doctors came out in the day, they handed them a carton of Lucky Strikes and said, "What do you smoke?" And the doctors would go, "I guess I smoke Lucky Strikes." Okay, 4 out of 5 doctors would say that, but it was not a valid survey for that. If you can't find bias in your survey, look harder. It is always there, always. I spend more time complaining about bias than anything else. Access. If you are just polling this crowd, you're going to get a great view of the DevOps engineering and SRE space, but you're probably not getting to get the same view of an end user space or the management executive space for that. Questions and interviewers can provide their own biases, and that bias can have some really interesting access. These are the four that you most often run into: cognitive, selective, recency, and status quo. For instance, yesterday you weren't married, today you're married. 2 weeks from now, you better have had 14 wedding cakes available because you're going to be adding people, right? Okay, once again, it is very easy to go out here with statistics and say, this is perfectly valid. You went from 0 to 1, so you're going to go from 1 to 2. Doesn't quite work that way, but nonetheless, we keep that. So if there's no recent outages, we tend to think that there are no outages going to happen. You know, and I know, that doesn't work that way. It's a flip of a coin. It is a probability-based function. Probability is based on statistics, but just saying everything's working fine doesn't mean everything will continue to work fine. So, self-selection bias. This is where you pick people. And we'll go into a deeper study on this one. But for instance, you're going to look at a new deployment tool. You only ask the senior engineers to look at the tool. You will get a different result than if you asked the junior engineers and the senior engineers to look at the tool. You know, if I talk to people that I used to work with in Silicon Graphics and you say, for those people, how important was C++? They'll go, oh my God, I couldn't have lived without it. If you do the same thing today, you'll find that nobody even knows what C or C++ is or how to write it. And so the recency, the self-selection bias becomes really important. So confirmation bias is my personal pet peeve, and is the wording of the questions leading to skewed answers. How happy are you with the new tool, the new and improved tool? Will lead you to say, oh, the new tool is good because they asked you specifically what was good about the tool for that. How beneficial has the tool been? These are confirmation biases. And confirmation bias is not just the question, but it can also be in the interpretation for this. You know, we went through this wonderful pandemic thing. Everybody worked from home. We had this return to office space. Companies, large companies set up policies that said this is what return to office looks like. So imagine the question that says, confirmation bias-wise, how, or quote, do you understand the return to work policy? And the return to work policy is published and has been talked about and everybody's shown slides and so forth. And so the answers come back 86% say, yes, I understand the policy. And the result is pointed out as 86% of the people approve of the policy. Okay, that's a shift and lie on confirmation bias. So, recency bias, we talked a little bit about this. How happy are you with the last deployment? Not all the deployments over time, but the last deployment. Did the last deployment work well or not work well? So this recency bias can hurt you one or two ways for that. But done basically, you know, the last question, Q3, most recently, how beneficial has this tool been? And that's combining a recency as well as this bias for reliability. It's leading questions. And then finally, status quo bias is the reverse of that. You're trying to disprove the functionality. How disruptive was the new tool? Maybe you had to rewrite automation scripts, and it becomes a very disruptive environment for that. And now we get into pictures. I have seen so many graphs today, I'm almost afraid to show graphs for this. This is actually an approval rating that was put out by an SRE team. And anybody notice something? It's missing a few things. You're right. There's no axis. I don't know how long this was. I don't know what the range is. But by God, this line looks really, really good. Okay. So let's take another look at this. This is the exact same line. I now have a range 0 to 100. Wait a minute, what's this thing for these? These are called cutouts. And they're used a lot in publications for graphs. And you have no idea how big this cutout is. It doesn't tell you. And by the way, it doesn't give you these nice, cute little lines to show you what the cutout is there. It just will draw the straight line up and down for this. This cutout is hiding the information about where that line actually falls on the curve. And since there's one above and one below, you're really, really messed up for that. Okay, well, let's fix it again. Okay, so here's the line. Oh my gosh. We have a scale that said how long it took. I don't know whether it was weeks, months, days, whatever, nonetheless. And I've got a scale over there. Anybody catch the trick on this one? Yeah. This is a log scale. It's a log 10 scale, to be precise. And again, what I'm looking at is this 10 to 100, but most people are very bad at estimating what the value of a log scale looks like. And by the way, this is the actual line. And the numbers ran from 37.4 to 41.2 over that entire time frame. It's pretty much a straight line over a 14-month curve. Yeah, it went up a little bit. But if you think about what that original one looked like, my God, they did a massively cool improvement job. Graphs are used to lie more than anything else in statistics. If you see a graph and it doesn't show you the scale, the range, and the number of items that are there, it's a lie. So if you want to lie, you just saw ways of doing that. And I will tell you that most people will never catch on that you're lying. Okay, so the next thing is you can strongly suggest the answer. And this is a category that is really kind of tricky. So each of these things is actually a doubling in size. But rather than just double the bar, I actually move the bar. So it goes from 1 to 4 to 16. And this is where everybody fixates. Just to make life more interesting, I have a nonlinear scale as well. And so everybody immediately goes, oh my God, look how good this one is. And just to make it more, you can do this in a one-dimensional picture approach. Same thing, because now everybody completely ignores those two little pastel bars, which barely show up on the screen, and go, oh, look, this must be really good. He's smiling, he's happy, and it's huge. It must be great. This is one-dimensional picture. Again, advertising uses one-dimensional pictures all the time. So if you want to lie, find something cute. Pixabay.com is a great place for finding cute pictures that have no royalties for this. Okay, now, this one goes back a little way. This was 2008, 2009 timeframe. This is showing the number of percentage of users on the various PlayStations at the time. And the article points out how poorly this Wii was doing compared to everybody else. They don't tell you the things. At that time, there were 50 million Wii owners, 30 million 360s, and 20 million PS. If you look at 6% of that number, which is where this comes down to, it's 3 million, 11% at 3.3, 10% is 2 million. This graph is completely wrong. It is comparing unequal things, and because they're making them as percentages, they're telling you that they all work perfectly fine. And that's not the case. It doesn't work that way. If you had added them all up, then you would have seen, for instance, that this still would have been higher, but we would have been just below the 360 model, rather than being on the bottom of the line. Now, for the US source, the Nielsen Company is rather interesting. If you look at their data, they did exactly what I talked about. They add them all together. They show the percentages comparatively across those pieces for this. This came out in a very well-respected magazine. And they were trying to prove that that was really important because obviously nobody was using this thing. Not correct. Over here, pie charts. Pie charts, if you're in percentages, should equal 100%, right? This one is 230. There's a big problem with this because even though they are loosely comparing driver opinions, no gas tax, wants better road, ban EVs. They're all in the same category, but they have no relationship to each other. Putting them in a pie chart makes it look like this one is the most important thing and banning EVs is the least important thing. Again, no correlation that happens across that, which of course leads us to correlation. If B follows A, then obviously because A is causes by B. So correlation is something that is endemic to people. You want to prove that you got too much automation, your DevOps team notices that the number of deployment automation scripts increase, the number of incidences in production increase. Does that mean that automation is causing the problem? No, it doesn't. You could be writing automation scripts to handle a problem that is causing production problems to begin with. There are no correlation aspects inside of that. And when you get into this, correlation is not causation. Correlation is important, but it's not causation. Causation, sunshine, correlates to people eating ice cream. Sunshine causes sunburn. These are kind of the different structures inside of here. What happens is that we have all these other things that happen. Confounding variables, reverse causation, bidirectional causation. Let's look at reverse causation, for instance. There is a 100% correlation between divorce and marriage. There is not 100% correlation between marriage and divorce. And by the way, just to add to that space in here, if you get married, you've got two choices. You're either going to get divorced or you're going to die. What's your choice? So keep that in mind. And that leads me to my favorite of all time example of correlation issues. Okay. This is marriage and beer sales over a period of time. Does drinking cause marriage, or does marriage cause drinking? And actually, the answer is neither in this case. This is what's called a confounding variable. Population increase and age of population increased over this period of time. People started drinking more. People got married. There were more people to drink. There were more people to get married. There were more people buying cars. There were more people doing all these things. It's a confounding variable. This is A to B and C to B, but A to C is not valid. So confounding variables get used a lot. And unfortunately, in the observability space, we use confounding variables all the time, okay? So here's one of my favorite ones of those for that. You do a deployment and something goes wrong with production systems. You immediately suspect the deployment was wrong. Did the deployment cause the problem? I can argue either way, so feel free to grab me afterwards and argue your side of the case, but I can argue either side of this case. I can clearly state that putting the new deployment caused a problem, but I can also point out that the problem causation item was not the deployment, but something within what was deployed. But I can certainly point either direction for that. And by the way, this also goes into the 4 out of 5 dentists recommend CREST type of models. Similar structure, but when they're going through this, they're actually looking at a confounding variable structure because when they did the survey, CREST was at the time the only toothpaste including fluoride. And so they were looking at this and saying, dentists believe that fluoride helps teeth, therefore dentists prefer that you brush with CREST, and therefore dentists approve CREST. No, dentists approve fluoride. That's what it came down to. Data dredging and p-hacking. is getting a little bit into some of the statistical aspects of this. So data dredging, looking through large volumes of data to find something that you can present as statistically valuable. P-hacking, manipulating the data choices. I did this with a little survey. For instance, I p-hacked that survey. P-hacking can also going into establishing my theory such that there are no valid null theorems that match that data. And Tyler Vegan, tylervegan.com, is probably the leading guy that plays around with this structure. So this, instead of starting with hypothesis testing, he grabs huge data sets and finds things that match up. And that becomes a really fascinating practice. If you're here for my Ignite talk tomorrow, I'm going to go through probably about 18 of those really weird off-the-wall correlations that happen. But this is a data dredging model. This came out in a, I'm trying to remember, I try to cut out things so I don't pick on companies too badly. But they were going, who cares about this global warming thing? Because look, over this period of time from 97 to 12, it all averaged out. There's no difference. What's the big deal? Okay, well, that's because they grabbed a little tiny block inside of the overall structure. And they very carefully pick out a block that they could say, oh, it starts here and ends here, and this is therefore, that's what all the data looks like. But you can pretty clearly see that over a point in time, that's not what the data looks like. But by selecting correctly their data choice, they can make their statement and their opinion. Okay, my one politics, unfortunately, whatever. This is March 2nd, 2024. 82% of the US understands this was a rigged election. That was the quote. Now, my statistical thing went off and went basically, I'm sorry, I am a US citizen. We don't have 82% of anybody that agrees on anything anymore. So this got to be something on. So I went looking for the data. So here's the data. After this, before this, because of this, for this. First of all, Public Religion Research Institute. I think we might have a selection bias, first of all. By the way, this was published in 2021. They actually did a really good job. If you go read through the structure, it's actually really well done and really well presented. So how did they get that 82% number? Well, right here, there's this thing called Most Trust Fox News for this. And 47 plus 35 equals 82%. So if you go through this, Farce Right News at 90, trusting Fox News completely is roughly 66, which means 54 people out of 66 believe this, or 54 out of the total sample size are roughly 2%. Totally valid data misrepresented. If you want to lie with statistics, find the data that you says what you wanted to say and present it as a fait accompli, and no one will generally question you, except people like me, because we like to poke holes in numbers. So the answer is pointless without the question. If you remember in Hitchhiker's Guide to the Galaxy, the final question, when they pull the little Scrabble tags out, what do you get if you multiply 6 times 9? And the answer was 42, which is absolutely correct, base 13. So keep in mind that what you see may be totally correct, yet totally misleading. Whoops, he hit the wrong button for this. So, simple ways. Statistics are pretty cool. I wouldn't believe how they were cool until I did the talk last year, and it really got to be kind of cool doing this. But look out for conscious and unconscious bias. Bias is not always conscious. People ask questions to get answers that they think are important. If you can reword the question in such a way that you can reverse its meaning, you have a bias. Keep that in mind. Data dredging, finding the data that says what you want it to say. You can use that in both your use, but look out for it in other people's uses. All this unclear or incomplete. No axes, No way for that. Confounding variables. Correlation is not causation. Humans love to find patterns. They are really good at finding patterns. And showing pattern curves, people will go, oh, they must work. Look how this one goes up and this one goes up and this one goes down, this one goes down. And they're not necessarily correlated at all. But keep that in mind here. And then pretty pictures. We really like pretty pictures. If I had thrown kittens up here, everybody would be going, oh, look how cute the kittens are. And we saw that, for instance, with people introducing their puppies and their dogs, all these different pieces. Pretty pictures matter for this. Actually, accordingly, numbers do lie. It's not true. The choice of numbers lies, and the representation of numbers lies for that. And then, if you notice, I've had these little pithy quotes underneath here. Statistics are history. History is written by the winners. It's my personal quote for this. Statistics are collected by somebody who is out to win. So keep that in mind. And with that, you can find me. This is my LinkedIn site. There's my LinkedIn. There's my GitHub. My slides always live on GitHub, so you can always find them there as well. And with that, I'll open it up for questions. Actually, I think I'm out of time. Ta-da. And just to let you know, the last question, if you've got any questions about everything, this is the great place. And start with how to lie with statistics.
Thank you very much. That was a fantastic talk. Thanks a lot, Dave. If you have any questions for Dave, you can catch him. I guess he will be around tomorrow as well, and also for the rest of the day.
I'll be here tomorrow.
Okay. So for the rest of the day, at least. So yeah, thanks again. We will move forward with a quick break, and the next talk here will start at 4:30. It will be the last for the day. Thank you, Dave.
Thank you. Thank you all so much.